Moritz Hardt, who's going to be talking about, is your model predicting the past?
Thank you very much. Yeah, so this will be short. This is kind of a chaser to Huangqi's talk. So if you watch this on YouTube, first of all, hit like and subscribe. Show the Simons Institute, our sponsor for today, some appreciation. Also, click on the video that Huangqi just, or the talk that Huangqi just gave. So this will be self-contained, but it'll make more sense. It'll resonate more with you after this wonderful talk. So what is this about? Okay, so if we zoom out a little bit and we try to figure out what sort of we're really talking about at this workshop, it's about prediction, it's about when we should use prediction, it's about how we should use prediction. And so here is what I think is really core to many normative debates about prediction, and in fact not new. It's this question of when are we justified in using statistics to decide about individuals, okay? And this is a political battleground and has been since at least Quetelet and his social physics from the 19th century, and the idea that human populations are distributions and they follow laws, and that these laws are some kind of normative benchmark that you judge individuals against these statistical laws, that sort of led to Galton and the eugenicists to sort of make that normative benchmark like something that you wanted to improve upon. And so this is it's been going on for a while, right? And we're still in this sort of debate, in my opinion, right? It hasn't changed all that much if you go back in history. And so we're talking about this sort of tension between aggregate patterns that we find in distributions and individual life trajectories, right? And so proponents always do this kind of sleight of hand, proponents of prediction, whereby they say that these statistical risk scores really give you a look into the future of an individual life trajectory. And I want you to sort of critically examine your typical argument in favor of a predictive tool. It always hinges on some implicit assumption like that we're forecasting an individual life trajectory, and hence we're entitled to intervene in that person's life. For instance, by putting them in jail in preparation for their trial, right? But if we're not predicting an individual life trajectory, if we're maybe just predicting what school your parents chose for you, the whole sort of argument in favor of prediction kind of breaks down, right? And so this is what sort of others point out, that while prediction punishes or can punish individuals for circumstances outside of their control and things that predate their own agency, okay? And so in this room, there have been many in the sort of multi-calibration community to ask, what are individual predictions, right? How do we get better at making these individualized, highly individualized forecasts? And in my opinion, multi-calibration is sort of a framework to approach this ideal of an individual prediction, whereby you just kind of make your predictions more and more fine-grained until you can really treat them like individual forecasts, and then everything sort of works out. I'm going to do the opposite in this talk. I'm going to ask what is blatantly non-individual, okay? So I'm going to ask what predictions are not about the individual, but rather about their environment. And when are we actually predicting the environment? And you saw in Huangqi's talk one beautiful example. So I'm going to give you sort of a more general way to think about that, okay? So this distinction between individual versus environment is certainly also not new. It's actually fundamental to the theory of equality of opportunity. And one line of work I really admire in this space is John Roemer's formal definition of equality of opportunity from the late 90s, which basically says so much as to say, equalize rewards or equalize allocation based on individual effort relative to the individual's type. Okay, he's saying if you're in the 90th percentile of effort relative to your type, which I'm about to tell you what that means, you should be entitled to the same outcomes regardless of type. Okay, so the 90th percentile of effort always gets the same regardless of type. Okay, and so this all hinges on, effort is sort of the more easy part to define, right? It's like maybe your test scores or something like that, how much work you put in. These are sort of the individual features. But what is type? Okay, and Roemer actually spends a lot of time over the years sort of going back to this definition, revisiting it in light of like new understanding. And here's something he wrote in 2000. He said, a type groups individuals of similar circumstances where circumstances are those aspects of one's environment, including perhaps one's biological characteristics, which are beyond one's control, okay? And so for instance, one thing he struggles with when it comes to type is race a part of the type, right? Or is that like an individual feature? So it's a challenging distinction to make, but it's absolutely fundamental to this kind of theory and this our understanding of equality of opportunity. Okay, and so I'm going to be a little bit more pragmatic about it. Okay, and I'm going to lean on sort of the crutch of time. Okay, and I'm going to sort of bootstrap this distinction between individual and environment, just using the idea of like what came earlier. Okay, so I will say though that like this whole theory of like social constructionism, you know, certainly challenges this distinction between individual and environment, right? Like what is, for instance, religious affiliation, right? That's like some like collective practices of your parents and they baptized you when you're early or something, right? Is that really you're doing, or is it your parents doing, or your environment's doing? You know, who knows, right? So it's a social construct, and as such, it sort of blurs this kind of line, right? But let me try to approximate it for the purpose of this talk, because we're like kind of pragmatic machine learning people, with just the help of time, and that's why we called it, you know, backward baselines, or you know, backward features. We're asking sort of what are the features in your problem that came before the individual's agency, okay, and are hence sort of outside the individual's control, okay. And so examples are your age, race, biologically assigned sex, place of birth, various decisions your parents made, like which school you go to, etc. Okay, and we'll be sort of like a little bit fuzzy about exactly what we throw into the background features. Okay, so it depends a little bit on the application that we have. Sometimes it makes sense to include sort of all demographic features, things like marital status, even if like that's technically something you can, you know, manipulate. Okay, good. So what am I going to do in this talk? I'm going to try to convince you that this distinction between individual and environment is absolutely fundamental to our discourse about prediction. And I'll tell you a little bit about how you might go about defining it and how to evaluate it empirically. And then we'll look at some data sets and see how that plays out. And then I'll end on like a discussion of how this should sort of inform our debates around prediction and risk scoring and the use and limitations of prediction in various settings. Okay, people still on board? Good, great. Formal setup, okay. And by the way, this is joint work with Michael Kim, in case I missed it in the beginning over my YouTube announcement. So whenever I get stuck, you know, I will point to Michael for help. You know, and you should ask all the tough questions to Michael, okay? So formal setup, it's a standard just prediction setup, the one we've been using throughout this workshop. So you have like jointly distributed random variables, X and Y, expressing features and a target variable. And you look at a standard sort of risk minimization setup where you're trying to minimize some loss function over a fixed distribution. And we'll typically just look at a loss function as either squared loss when you talk about regression, or 0-1 loss when you talk about classification. Okay. And you know, just to recap, you've seen this many times. The optimal solution to this problem, if you're unconstrained, is the conditional expectation of y given x in the case of squared loss, and in the case of 0-1 loss, you round it. Okay, and that gives you a classifier that minimizes this loss, 0-1 loss. And we'll generally designate these background features. Okay, so Juanqui gave you an example of like what, you know, background features were in the case of Wisconsin public schools, and it depends a little bit on the application that we have, what constitutes background. And I'll denote these features by the letter W. Okay, and I think of X as sort of all your features. So I assume that the W is measurable with respect to X, so you can, like, you know, knowing X means you know W. Okay, so X encodes everything, and W sort of more coarse description of the individual. So you know, before Avi leaves the room, this is just for illustration. It's not part of the formal setup. It's just for the people in this room who like causal diagrams. I actually, you know, drew this causal diagram, and it's I made it prettier by you know, giving it a time axis below, and we sort of interpret this causal diagram like over the course of time, where these background features are sort of like assigned first, and then they have a chance of influencing the individual features and the outcome. Okay, so they're confounding the individual features and the outcome. and you know, X is sort of might directly influence the outcome, how much effort you put into something, etc. But this is maybe a helpful way to illustrate it. Okay. Is the formal setup clear? Nothing really has happened. I'm just like throwing in an extra random variable. Okay. And so this leads to this definition of backward prediction, where we say that a predictor F is a backward predictor if F of X is conditionally independent of Y given W. Okay. Does that ring a bell? This is basically what Huanqi talked about. Okay. Just so this is like, you know, when we did this, there's sort of the deuce thing wasn't quite as clear to us, and then it was actually like interesting to see this pop out of deuce. So we didn't sort of hack it. You know, it's just kind of like, you know, in some sense, Michael and I theorized this, and then we saw it in like the deuce case, like pop out very clearly, actually much more clearly than I had expected. So I didn't think that this would sort of ever be as crisp in a practical setting. Okay, and so the way I think about this is that conditional on background scores look random. Okay, so conditional on your background W, the scores are just, you know, a random variable that has no signal. Okay, again, you could look at just sort of the optimal you know, solution based on only the background features. This would be just the conditional expectation of Y given W. And same for the 0-1 loss. So we can in general talk about like what is optimal given W, and we'll use that. And as an example, the deuce risk score, as you just saw, is independent of student dropout conditional on school. Okay, so the deuce risk score is a backward predictor. Okay, and I think of also backward prediction as like sort of blatantly non-individual, right? And I sort of think of this as kind of a TCS move that I learned from the TCS elders, that if you're struggling to define a concept, you should start by defining what is blatantly not the thing you're trying to define. Okay, so this is a lesson I learned from like Omer and Cynthia, and this is like what you should be doing. I might be doing it wrong, but I was trying to sort of approach this question of individualized risk by sort of imagining what is the opposite, what is blatantly non-individual. Okay, and so this is trying to get an answer to that. So I like this picture, right? So here's the world according to backward prediction. Okay, so Megan.
So sorry, I'm a bit confused on how you're defining background with respect to time. Like school is chosen after birth, right? So
well, but I think sort of, you know, again, I will interpret it liberally. So the question is, why is, you know, school background if it's like technically after your birth? That's why I said we'll sort of like, you know, things that are sort of plausibly outside your agency, right? Like a decision your parents made for you, right? Or a decision that sort of is strongly constituted by your environment. Right? Good. Your sort of parents choose where you live. That narrows down the school. You can't just go anywhere, etc. Right? So, good. So here's what the world looks like to backward predictor. Okay. As in our example, there's the 0.5 school, and there's the 0.9 school, and there's the 0.1 school, and you can go to the 0.7 school. But given that you go to the 0.7 school, you know, I learned nothing. You know, Nati is a 0.3, Emily is a 0.7. It means nothing. I just look at it, and it means nothing to me. And this is sort of, interpret this from the perspective of the teacher. You know, I walk into the school, presumably I know where I am. Okay, I know I walked into the 0.7 school. Okay, I know I'm not in this school, right? So by the time the teacher walks through the door, all signal is resolved. So at that point, the teacher only sees like random numbers in the classroom. Okay? There's no more signal in it. It's just like, it's as if you're staring at like a random like labeling of the students.
maybe I'm not quite. I just want to make sure I'm understanding. So I guess the risk prediction is independent of your individual features, but that doesn't necessarily mean that like what happens if there's an intervention is independent of your individual features. So like the teacher looking at
excellent point, Charlotte. So hold that thought. So what does it say about intervention? Excellent point. Okay. What backward prediction says about intervention? Okay. And this is like I'm extracting out this observation from this paper with Huanqi, Tolani, and Rediet. Here's the thought experiment you need to do. Okay, and it needs some assumptions, but then it actually says an awful lot about intervention. It actually says almost everything about intervention. Suppose now like a setting of the background features defines a unit, like a school, right? Some like well-defined social group. Okay, And assume the following: assume the unit has at its sort of dispense an intervention that improves the outcome at a fixed cost. Okay, so schools have a budget, and they know some set of interventions. Let's say 1. It could be great, it could be bad. It doesn't matter. They know an intervention that improves the outcome at some fixed cost. Okay, and let's make one more assumption. Let's assume that the unit targets these interventions at least as well as random, given its budget. Okay, so the school, principal assigns this intervention at least as good as a random allocation. So they're not like blatantly incompetent. They know like roughly who to like intervene on. Okay, so they're better than random, at least as good as random. Okay, not necessarily strictly better, but they're like no worse than just like randomly throwing out the intervention until the budget is depleted. Okay, these are 2 very reasonable assumptions in my opinion in most settings. Under these 2 assumptions, it follows that targeting the intervention based on a backward predictor cannot lead to any improvement. Is that clear, this proposition? I'm writing it informally, but it's a lemma, if you will, or like a proposition. Okay. Under these 2 assumptions, that you have an intervention of some strength, you can target people at least as well as random, then the backward predictor cannot give you any improvement. Why? Because the score is random given the unit. Okay, so at the level of the unit, this targeting based on the backward predictor is like at least only as good as targeting randomly. Does it make sense? So the beauty of this argument is, I know what you're thinking. You're thinking, well, wait a minute, it could still be that interventions work great, right? And I agree. But I'm saying the backward predictor wouldn't help you with the intervention, right? It could still be that schools have like an amazing intervention which completely prevents dropout. Could be. But the backward predictor will not help you at all in targeting that intervention. Does that make sense? Okay. Yeah, this took me a long time. Like we kept staring at the data, and this sort of had to grow on us, I think. Like it took us a while to like figure out that actually under some very weak assumptions, this resolves the question of interventions. We kept thinking like, what about interventions? And like, it actually resolves that question. We just didn't see it at first. Okay, good. So how can we now get, I'm going to get into some slightly technical stuff. It's not super exciting, but how can we measure the strength of backward prediction? The first idea that you might have is just train a predictor based on only background features, see how good it works. Okay, just fit a model based on W, see how well it works. This is reasonable, but it's actually not the only thing you can do. There's another thing that makes a lot of sense. Specifically, given a risk score, given somebody presents you with a risk score, like the DO score, you can train a model based on W not to predict the outcome, but to predict the score. Okay, so you can ask like, how well can I predict the model F given something that only uses W? And the appeal of that is that it doesn't even need the target. Okay, you don't even need the outcome. You don't need to wait around until students have either graduated or not. You can instantaneously sort of check how much their background prediction is going on. Okay, so this does not even need target variable access, and as a result, it sort of makes auditing a lot easier. You don't even need outcomes. Okay, and so oops. Okay, so let's give them some notation. So I'm going to use these triple notations. So yeah, Andrew.
Is the previous task, is that related to like in causal inference, just measuring confounding?
Yeah, I think you can sort of, if you think of the W as a confounder, right, you want to know how much like, how much confounding. I mean, a lot of these things, this is relatively, because the setup is like, you're just introducing an extra feature, right? So all sorts of things are going to be like formally equivalent. I'm just interpreting it in a certain way. And this context. Okay, so let me give some notation for this. I'm going to call XYY the experiment, where you train on data generated from X and Y, and you evaluate on the target Y. Okay, and there are 4 other things you could do. Okay, you can train on WY and evaluate on Y. You can train on WY hat, so you train to predict the predictions, and then you evaluate on the true labels. This is the second thing I mentioned. But you can also choose to evaluate on something else. Okay, so you can choose to evaluate on the predictions instead of the target. then you get this y hat, where you train on the true labels, and then you evaluate on the predictions. And finally, the other reasonable thing that you could do is you can train on the predictions and evaluate on the predictions, okay? So these are the four things, just sort of like mechanically, the things you could implement in sklearn, okay? So you can, like, you know, if you imagine fit and predict, you know, this is like, you just plug in the labels. This is how I remember it, okay? So there's four things you can implement with fit and predict. You just put one thing in fit and the other in predict, okay? And so this is how I remember this, okay? This is a little bit sketchy, but okay. Good. Fortunately, things simplify a little bit, assuming the predictor is weakly calibrated, according to some Michael Kim definition of weakly calibrated. It's actually the space collapses a little bit. So wyy is equal to wy hat y, and wyy hat is equal to wy hat y hat. And so it only matters what you evaluate on, okay? It only matters what you put in the third letter, and it doesn't matter what you put in the second, okay? You can think about why that is. It's actually a good exercise for the calibration geeks, okay? And, or you can just like do it in Python and see that it's true, which is what I did, okay? So, and so also the other thing is for squared laws, it gets even easier, because for squared laws, the sort of XYY loss is equal to the WYY squared loss minus the WYY hat squared loss, okay? So these things kind of add up to the same thing. Now he's getting nervous.
This is assuming you have data or
The population level things. The population level, yeah. Population. This is all at the population level. Yeah, good. And so let's look at empirical evaluations. And so here we actually evaluated backward baselines. So these like four ways of doing it on large longitudinal panel surveys. And why did we go to panel surveys? Part of the real reason was that panel surveys, so these are surveys that survey the same individuals over multiple time windows. They're usually very precise about the temporality of the variables, okay? And they very cleanly separate sort of demographic variables from like things you did in a certain time period. And that sort of gives us a very clean empirical evaluation. And actually, as a side note, go to your favorite machine learning data set and try to find out if the target variable came before or after the features. And funnily, it's often not clear at all. If you have something like fraud detection, are we looking at transactions where fraud has already occurred, or are we looking at transactions where fraud had then occurred? Okay. Little sort of side note that like machine learning people usually don't even document whether we're predicting something that has already happened or something that's going to happen. Panel surveys sort of solve that problem because they're very clear about it. That's why we use it. And so one big well-known panel survey is the medical expenditure survey, MEPS. It's a large longitudinal survey of individuals, households, and healthcare providers. And it's aimed at providing insights into healthcare utilization. We turn this into a prediction task by basically taking the feature from one wave of the survey and the outcome variable from another wave. And here in this case, we looked at everything that was designated demographic by the survey. And we, at the target variable, we took some threshold of total healthcare utilization in a year, okay? So the data is basically a bunch of demographic things, a bunch of things you like medical doctor visits you did in a year, and then your total healthcare utilization at the end of the year, okay, which we're trying to predict. Good. What happens here is the summary of all these things. So these bars are the different baselines. So blue is the real thing where you take all the features. Red is where you, or the middle is where you take, you just train a predictor based on W of the outcome. And orange is where you predict the label, okay? And so what do we see? If you just take age, that already like gets you like a pretty good predictor. So healthcare utilization, age makes sense. If you throw in race alone, gives you a little bit of signal. Age and race is pretty good. If you take all demographic variables, you basically get most of the way to the all features, okay? It's not as striking as Deuce, but it's similar. That like taking all demographic features gets you basically closes the gap with all features. Okay, so most of the signal doesn't come from what you did in a year, but from what had already happened a long time ago. 5 minutes. Okay, great. Okay, and so this is for 3 different models: logistic regression, gradient boosting, and random forest. Okay, Emily.
Features,
Those all features.
The past features at the stage
This is the second baseline where you evaluate on the predictions. This is evaluated on the true labels, this is evaluated on the predictions. Okay, so this is the thing you could compute by only having predictions and no outcomes. Okay. Good. So you see, it's not maybe not quite as striking as dues, but although it's like pretty close. Most of the signal is in background. All right, and you do get very little power out of like things you did in a year. Here's the same thing for square loss. It's just sort of similar, except that now random guessing is just like 0.25. And now you see this fact that I claimed, which is that the orange, the red minus the orange is the blue. Okay, so this is what I claimed, that for like squared loss, there's really only one thing, right? Or like two things. You know, the red minus the orange is the blue, and so you can forget about one of them. Okay. So for squared loss, things are very simple. Okay. Questions about these plots? Now do you look a little puzzled? I didn't divide the squared loss by 0.5. This is how I roll, you know. Yeah. Now he's speechless. I've never seen that. You can also look at you know, RC curves, and you just as a visualization of how predictive background features are, you know, and you see for all demographic, these curves are pretty fat. It doesn't have to be that the orange thing is below the blue for reasons that you can think about. Okay, there's another panel survey. I'm going to wrap it up soon. Another panel survey, SIP, Survey of Income and Program Participation. It's again an important longitudinal survey, but done by the U.S. Census Bureau. That's aimed. Yeah.
So, in some sense, how can it be, right? Like, of people in a certain age group, you know, there are the diabetics and the non-diabetics. How can it be that seeing the feature of diabetes doesn't help prediction?
So it's more like, you know, you should look at the features. I don't think there's diabetes is on there, right? So I think it's more like the sort of non-demographic features are things like how often did you go to the doctor, right? And so, yeah.
So perhaps the issue here is the feature.
So with all of these things, like one sort of takeaway that would discourage is to say, what if we collected even more data? Wouldn't this sort of like go away? And you know, it's just, I don't think so. Right? Like, because then, you know, like, yes, sort of the accuracy levels change, but why would you expect that? You know, if you throw in more demographic features as well, somehow the gap would change.
Or change the training algorithm. This multi-correlation.
So these are like tabular data sets. Can you change the training algorithm? These are tabular data sets. You pretty much get the base error. Like, I don't think there's any like fancy, like, you know, better model that would get you better accuracy.
But, sorry, can you repeat your point? So you're saying collecting the diabetes, you're against collecting the diabetes feature?
No, I'm just saying, like, this is not the sort of take. You can collect whatever features you want. I'm just saying, like, then, you know, give me the features you want and I'll make the argument again on your features.
Can you go back to, as he's talking about this, the previous steps?
No, there's no diabetes on the slides. It was
No, not diabetes, but like in terms of how well, I guess the question is it because you're doing so well for demographic features that, you know, you don't see the improvement because the way you're scaling things in some sense, you don't see the improvement by actually observing the medical features? Or is it because you're just doing very poorly anyway, so you know, there's just no signal in the this distinction? I'm trying to map it to these numbers and I'm failing.
So, I mean, first of all, like, diabetes is an interesting example because, like, the social determinants of health, you know, you can look at Nancy Krieger's book, and we could go on an argument of like how health outcomes are determined and where in which bracket we should put them.
I think it's very correlated with environmental factors, but still, it is not going to be determined by.
Right. So, you know,
if it's true for diabetes, I'm sure we can think of another feature.
I feel like this is part of the question of like, what do we throw in what bucket, right? And I feel like I'm very happy for you to, like, if you like go and you look at the MEPS survey and you change the feature partition, right? I'm not married to this, right? I'm giving you an example of like, I'm taking the classification proposed by the survey provider and showing you the numbers for that. You can here's like a defeatist, like sort of nihilistic take on all of this, which is you can never rule out that if you collected all the data in the world, you know, accuracy would be 100%. Right? It could always be that there's some like individual feature, like, the wrinkle on your shirt, right? Which gives you 100% accuracy. You can never rule that out. So it's like sort of like, sure. Like there's always a hypothetical individual feature.
Yeah, I'm not trying to say that we'll get to perfect accuracy. It's just that you're trying to make a point about these are predictor, kind of just predicting the past or doing nothing interesting. Whereas
It's doing something very interesting, right? Like background predictors are very interesting. They're almost more interesting than like individual predictors. So, okay, let me maybe go to the takeaway because, yeah. So SIP, same thing happens, okay? So let me say why background prediction is actually like a really fascinating thing and not at all sort of like not interesting, right? So here's the reason, right? So first of all, there are sort of 4 different kinds of reasons that I can imagine for why you should care about background prediction. The first is, well, is a normative reason. Interventions based on backward predictors allocate based on things that were outside the individual's control. And that sort of runs counter to some of our ideas about equality of opportunity, right? Second, there's this political and rhetorical issue of like, if somebody tells you they're sort of doing something because it's an individualized risk score, well, you should ask, is it a backward predictor? Because then that whole argument falls apart. And like backward predictors should not be sort of labeled individualized risk scores, right? And then from a policy perspective, we did this whole thought experiment of like what backward prediction says about interventions. And we found that interventions based on background predictors are no better than random once we account for the environment. Okay. And finally, they're also like sort of sociological explanations because they speak to the sort of the social constitution of outcomes, right? Like if you can really predict the target variable well from only like background features, that says the outcome that you're studying is kind of like a socially constituted. And that is an interesting fact that you discovered. Okay, so that's where I want to leave it. Thanks.
I'm sure there are lots of questions. I want to take most of the long ones offline, but if there's one short burning question.
Did you look at the case where you actually just like, so there's this policy implication of like not being able to target interventions. Did you ever look at the case where like for example, the panel data, if you like condition on a specific race and age, whether your predictor is doing anything within that that's interesting? Like you would expect sort of like if it's a true backwards predictor, then if I look at like just white men at this age, then I should have like an ROC of 5 or something like that.
Yeah. So I mean, first of all, yeah, for just age and race, you saw the plot. It wasn't all that good. When you do all demographic features, you get a lot of variance.
Oh, but not in terms of like predicting from those things, but more in terms of like condition, like keeping those things fixed and looking at your predictor and seeing like if I condition on a specific one of those buckets. Did you ever look at like the conditional ROC?
But basically, if your score is calibrated and it's a backward predictor, then it's constant in that case, right?
Okay, yeah, I just meant as a way of telling something.
Yeah. I mean, this is equivalent to one of these things, right? Yeah, I think with the experiment you're saying is equivalent to one of these things. That's correct, right? Like the predicting the labels is equivalent to like basically within each bucket you compute the mean, and if you had enough data, it'd be equivalent to like within each bucket, take the mean, look at what the mean is.
Okay, thank you, Moritz. Okay, so we'll see you back at 2 o'clock in this room, and don't forget to sign up for our session.
Thank you for all the questions.